Today we're going to explore a really interesting concept in cryptography, which is called secure multi-party computation, or we can call it as MPC in short. It is one of the most powerful ideas in the modern security. Let multiple people or organization work together on a computation without actually sharing the private data. We can think it as a collaboration without trust. Everyone contribute, but no one reveals their secret. So let us see, why do we need secure computation? Let us see a simple example. Imagine we have three companies. Each company want to know who pays the highest average salary. Each company has its own employee data, has its own records, and so on and so on. But obviously, no one wants to reveal their salaries to the competitors. So among three companies, the one company doesn't want to reveal how much do they earn, how much is their revenue, etc. and so on and so on. Let us take another example, which is about the hospital. Think about hospitals wanting to study the effectiveness of cancer treatment. They like to combine the patient data. That's how we know how what is the effectiveness, what is the cost, leads, everything. But privacy laws like HIPPA stop them from sharing the personal medical records. So the question is, how can we compute together while keeping the data secret? That's exactly where secure multi-computation makes possible. Everyone can take part in the computation and still protect their private information. The privacy is very important, but still they want to lead it. So let us see what is MPC in short. It is a privacy preserving encryption method. It allows several parties, let's say Alice, Bob, Carol, to compute a function on the private inputs such as f of x, comma y, comma z. They all learn only the final output, but no one learns anything about the others' input. So then they learn about the final output, but doesn't know the others' values. Like, see, for example, you have three-person, but Alice doesn't know what Bob is. Bob doesn't know what Carol is. They only know the final value, and that individual owns self values, but it doesn't know the other person's thing. So, for example, let us see Alice has the value as 10, Bob has value as 20, Carol has value as 30. They want to compute the total sum, which is they do the f of x, comma y, comma z, which is 60. All will learn the result 60. Alice will know the result is 60. Bob will know the result is 60. Carol will know the result is 60. But none of them know the other individual values. That is, Alice doesn't know Bob's value is 20. Bob doesn't know Carol's value, and so on. So that's the heart of MPC. Everyone learns the result, but secret always stays hidden. That is, they doesn't know the other individual's value, which is also that's a secret. Let us see a real world analogy. Imagine you and your friends each lock your secret inside a box. You then put all the box into a magic machine that performs calculations like addition, subtraction, multiplication, so on and so on, any hardcore count calculation without ever opening the box. Without ever opening the box, it performs the calculation. You and your friend keep your secret inside the magic kind of box, and then it gives you the final answer, but the individual secrets remains locked away. That's how exactly MCC behaves. Computation happens securely on hidden data. So how does MPC actually works? So let us see that. MPC uses special mathematical and cryptographic techniques. Let's discuss the three most common ones. That is secret sharing, yours guard secrets, homomorphic encryption. So first, let us dive deep into secret sharing. Each person splits their data into random pieces called shares. Each share looks meaningless alone. So, for example, let us say uh, you give a share 20,000, the other person gives a share 30,000, the other person gives a share 40,000. So, when it's not grouped, it's meaningless. When it's grouped, you know the result. But so each share looks meaningless alone. But when enough shares are combined, you get back the original value. So, for example, let us see example. If Alice's secret number is 10, she can split it into 4, 3, or 5 into 2, and so on. So each participant gets one share. No one can guess the real number from the single share. So everyone knows the number is 10, but each one gets a different split, a different share. So no one can guess the real number from the single share. but combining them reveals 10. That is the result. We'll know the result is 10. Using this method, computation like addition or multiplication can happen using the shares themselves. So at the end, the result will be known by everyone, but you don't know like which person got which number of share, which person got the less share, which person got the highest share. The result will be the same. The result, depending upon the result, only you split the shares. So let us see the second one, which is the Yours Gobble circuits. This idea came from Andrew Weir in 1982. It converts the whole computation into digital circuit. What is this circuit? A network of logic gates. Each gate is encrypted or garbled. Parties exchange only encrypted inputs and encrypted outputs. No one sees the raw data, but the computation still works perfectly. So the answer will be converted into a digital circuit. What is a digital circuit? It's a logic gate. Each gate will be encrypted, garbled. Parties exchange only encrypted values and encrypted output. They don't do the decryption. So no one sees the raw data. They only see the actual data, which is the computation still works perfectly. And let us see about homomorphic encryption. This is one of the most futuristic method that allows mathematical operations to be performed directly on ciphertext. That means you can add or multiply encrypted data without decrypting it. That is, you can add, multiply encrypted data without decrypting it. When you finally decrypt the result, you get exactly the same answer as if you had computed on a raw data. So, like when you finally decrypt the result, you will get the exact same answer as if computed on the raw data. So the data remains secure even while processing. So these are the three um, techniques. The most important technique, which is the secret sharing, yours, coupled circuits, and the homophily, which is also the futuristic method. So these are the main focused mainly three methods. So let us see a simple thing, which is how you will find the average. So basically, we know how to find the average is a plus b plus c by 3, which is the average salary of each individual divided by 3. But the everyone knows the average, but doesn't know each one's individual salary. The computation happens over encrypted of shared data. At the end, as I said, all they get is a final average value. No one learns the exact salaries from any other company. So this is combination with privacy guarantee. Each company has its own confidential data. The encrypted or secret share the average salary values using MPC. They compute the average value. As we all know the average default value, what will happen with it, and they compute it. At the end, they'll know the average value only. No one will know. A won't know the B salary, B won't know C salary, C won't know A salary. So it is a secret. The secret is remained the same, but the result is known by everyone. These is called as the shares. The shares is split into three here over here. So let us see the evolution of MPC. So first, the MPC is evolved in 1982. Who evolved it is Andrew Weir, the founder, who proposed the first secure two-party computation, which is also known as Yours protocol. In 1988, Ben or Goldwasser and Winchester extended this to multiple parties called as BGW. After several years, this Andrew Weir evolved it into a protocol called as BGW protocol, and later in 1990s to 2000, researchers worked mainly on MPC's fast and reducing network communication. And then we have and then later 2010 we have the SPDZ protocol made by MPC, practical for industries even in real time. Then in 2020, which is the current, MPC is being combined with blockchain and artificial intelligence, which is the most evolving technique for secure large scale application. So in short, MPC is stated as the theoretical idea, but no one has become a real world privacy technology thing yet. So let us see the modern application in MPC, which is where all we have been used MPC. So let us dive deep. We have used finance, healthcare, artificial intelligence, e-voting, and cloud computing. Let us in finance. So how MPC is used in finance? Banks can detect fraud or analyze joint trends without ever exchanging customer data. So the customer data is the secret here. Banks can detect the fraud and analyze trends without even exchanging the customer data. That is, they're keeping it private, but still they can detect the fraud and analyze the trends over there. In healthcare, hospital can perform collaborative medical studies while keeping patient information private. The privacy is being private here, but still the hospital can perform collaborative medical studies. And let us see how it is being used in AI, which is artificial intelligence. Companies train shared AI models without exposing the raw data. This is called as privacy preserving machine learning. So the privacy will be prevented, and always the company can train shared AI models without exposing the raw data set. In e-voting, voters' choices stay secret. That is who I am voting for. By the final election tally is accurate and verifiable. Here is where it is evolved. Like into each individual's voting will be secret only. No one knows who he or she voted for, but the final result will be accurate, tallied accurate, and verifiable. In cloud computing, MPC lets use a process encrypted data in the cloud. The cloud provider never sees the raw information. MPC lets use a process encrypted data in the cloud. The cloud provider never sees the raw information. So the secret is being maintained over here also. So MPC is everywhere. Everywhere you need the data privacy. Data privacy actually matters. So MPC is actually there in every application in our day-to-day life. So let us see a real world case study, which is Facebook's private. Real world example is Metask, which is Facebook's private lift measurement. Advertisers and Facebook's both have data. The one which is giving for the promotion, which is the advertisements, advertisers and the Facebook both have the data. Without data, you can't do anything. One who has saw the ads, the one who made the purchase using MPC, both sides, you know what, both sides they can compute how effectively ad campaign works without revealing individuals user data. Without revealing one's data, the advertise was a huge thing. So it was computed how effective an ad campaign was without revealing the individual's data. So the data is kept private all through it. So this is deployed at a massive scale today, showing that MPC isn't just theory. It's a production technology used by global companies. So everywhere the data is kept private, but still it led to a success, which is the campaign was successful and it was effective. So let us see about the advantages in MPC. So what are the advantages in MPC? So it protects sensitive data. It protects sensitive data during computation. So let us see the advantages of MPC. So protects sensitive data. It protects sensitive data during computation, removes trust and requirements. It removes the need for trusted third party, prevents data leakages. It prevents data leaks or insider misuses, and it enables safe collaboration. It enables safe collaboration even among competitors. Guarantees correct computation, and it guarantees correct and fair computation. The math ensures honestly. So in short, MPC builds trust through mathematics, not people. So I have a few interesting facts and insights about MPC. So let's think ahead. Like a human driver, MPC just doesn't react, it predicts. Just like how driver slows down before the curve, MPC anticipates what will happen next and adjusts controls input before errors actually occurs. That's why it is often called as look ahead controller. It's born from space missions. MPC originated in the 1970s from NASA, and petrochemical control research scientists needed a way to control complex interacting systems like spacecraft and refiners. The first large industry use was by Shell, and their refiners was called DMC, Dynamics Matrix Control. You know what, it is also used in self-driving cars like Tesla. Modern autonomous cars use MPC to plan trajectories in real time every few milliseconds, balancing safety, comfort, and energy efficiently. It helps the car see ahead and make smooth steering and speed decisions. It's like a mini AI controller on the car. MPC uses a model for the system like a digital twin to predict future outcomes. When combined with machine learning, it can adapt self-optimize, often referred as learning MPC. So it is also used in automotive industry and electric vehicle. MPC controls the steering, as I said, acceleration and braking by predicting the value tragedy for lane, keeping the obstacle avoidance. It is also used in aerospace. For example, in spacecraft attitude and tragedy control. As I said, NASA uses MPC to control satellite orientation and fuel consumption while predicting future disturbance like gravity or drag. So MPC is built through trust in mathematics and not in people. So it is used and evolved in all sorts of data, sorts of techniques, from a very small banking sector to a whole thing aerospace. So MPC is evolved and it is evolving through the thing. So at the end, MPC built trust through mathematics and not through people.